Pintz seem to do even better. Well, I think it's
okay.
246.
Good afternoon, everybody. I'm supposed to be charging the chairperson of this session. I'm Hu from KAIST. And the first lecture will consist of 3 short lectures by the following 3 people. Okay, the first speaker will be Professor Dan Goldston of San Jose University. And the second people will be Professor János Pintz from also San Jose State University of America. And the last one will be Professor Cem Yildirim of Goldston University of Turkey. Since we are supposed to have 15-minute break, so after the talk, if you have some questions, why don't you personally ask during the break time, okay? So let's get started.
Thank you for the introduction and the invitation. We're going to have 3 15-minute talks, so I have to talk really fast. And Pintz is actually not from San Jose State. He's from Rene Institute in Budapest. I'm going to talk really fast, so you can't really read the formulas at all. So you shouldn't even really bother. That all, even if I didn't have to. But they're mainly just for me to keep place where I'm at. So anyhow, what I wanted to talk about today is how this GPY method arose. And if you read about it now, it's pretty much an exercise in Selberg sieve. And the recent results of Maynard and Tao pretty much couldn't be done without using the Selberg sieve as the method of choice. But the GPY method didn't actually start with the Selberg sieve. In fact, the Selberg sieve method sort of came about in a series of papers which we call GGPY, which the extra G is Sid Graham. And the GPY method actually came out of a 1965 paper of Bombieri and Davenport on small gaps between primes, which actually came out of the original work of Hardy and Littlewood in 1923, and some unpublished work that they did. So in that 1923 paper, they made some conjectures like this first one, which is a prime tuple conjecture. It says that you can actually get an asymptotic formula for the number of times that n plus h, n plus h2, h1, h2, so on, are simultaneously prime. There's a certain density function, which we call the singular series. And in the case of just pairs of primes, that's an asymptotic formula for the number of times that m and n plus k are simultaneously prime, or the number of times that p, the difference between 2 primes is k. We can't actually prove any of these conjectures, these asymptotic formulas. We're just at the beginning stage of even seeing that they are actually asymptotic to something going to infinity in some cases. So Hardy Littlewood actually had a second method where they actually were trying to prove something rather than make conjectures on this. And so the average gap between primes is log of Pn. The difference between 2 consecutive primes is log of Pn. So you try to see if you can get primes infinitely often that are less than that average. And so the method that Hardy and Littlewood came up with, and I'll be using the notation of Bombieri and Davenport, is you look at this exponential sum over primes, where lambda is the von Mongold function. It's log of p of n is a prime or a prime power and 0 otherwise. But you should just think of this as an exponential sum over primes. And so what you do is you absolute value square this exponential sum, hit it with e to the minus k alpha, an exponential, integrate it, and it pulls out the terms when n and n plus k are both prime, which is what we're interested in. So then you have to approximate this exponential sum over primes. And what you'll notice when you do this is that it has spikes near fractions, particularly with small denominators. And the reason that that happens is that the exponential in here can only take on q different values when in here when n is, depending on what n is congruent to mod q. So you split up the sum. The primes are now summed over an arithmetic progression. And if we assume that the arithmetic progressions are all even, the primes are distributed evenly among those arithmetic progressions, then we can assume that this sum is the same on each of them, and you get a spike, basically. An exponential sum that's just geometric as spike, and an amplitude that's well known. So then what you do is you do what's called the circle method. You now split up the interval between 0 and 1 into little intervals. You put each spike onto each of the intervals individually, and then you add it up over all the fractions up to q. So that's our approximation. If you now plug this into that formula, you actually get the right answer. You get the correct thing for what you expect for twin primes, which isn't surprising because that's where the conjecture actually came from in the first place. But on the other hand, the reason the circle method fails to do the problem is if you actually just try to use it to count primes themselves, it gets the wrong answer. So if you just look at that exponential sum over primes squared, then by Parseval and prime number theorem, it should be n log n. But when you look at this approximation, it's only basically n log q, the size of the largest denominator of the fractions, or n over q, which is always at most half of this. And that's what we call the minor arcs. You basically don't get the contribution of s completely from the approximation. So here's what Hardy and Littlewood did and Bombieri Davenport followed, which is instead of trying to look at an individual difference between primes, you try to look at a whole bunch of differences between minus h and h. You square this exponential sum. Everything's positive. You therefore try to get a lower bound. You can throw out any part of the integration range you want because it's positive. So you integrate over what are called the major arcs. You put in your approximation. You square it out. You get a main term. You get a cross term, which if the arcs are small enough, and if the primes are evenly enough distributed in arithmetic progressions, which is a theorem called the Bombieri-Vinogradov theorem, is an error term, and then you get this error term squared, which is positive, so you can throw it out. So basically, and it turns out that the best exponential sum to hit it with here is actually the simplest one. You go through this whole thing in Bombieri and Davenport proof that there were infinitely often primes that were less than or equal to half of the average spacing, sort of a classic result. So now let me tell you the 10 steps it takes to get to GPY from this. Step one, first thing you do is you throw out this support on the spikes. So rather than having each spike having its own little interval it lives on, we just let them overlap each other. And there's really no good reason to do that, but we did it anyway. And then what happens is when you work out this approximation, it turns into an exponential sum. So this exponential sum at the bottom is trying to behave just like this exponential sum. So that's basically saying that lambda itself, our detector function for primes, is behaving like this arithmetic function. And this arithmetic function has a main term when you expand it out, which is basically this divisor sum. It's a sum d divides n over divisors smaller than q. And it's been smoothed a little bit. But in elementary number theory, of course, one of the things you learn is the von Mongold function has its own divisor sum. So the whole point of the circle method was that you simply truncate the divisor sum for lambda, and with divisors less than q, and you smooth it a little bit. And therefore, it makes sense to sort of study this approximate prime, I'll just call it approximately a prime. And the viewpoint is it should behave just like primes, although we can't usually prove it. So if you then go back, you can prove these Hardy-Littlewood formulas for this approximate prime, and you get the right answer as long as the R isn't too large. You get a result for when you have approximate primes differing by k, and you get a result using Bombieri-Vinogradov theorem even when one of them is a prime and the other one is an approximate prime. But you still have the basic problem that when you try to count primes with this approximation, you still don't get the full contribution. That was step one. So step two, you replace the rest of the circle method with, with the following inequality. You look at psi of x is the number of primes up to x. So you look at the number of primes in the interval between n and n plus h. And then you look at the number of approximate primes, and you just look at the difference squared, and that's greater than or equal to 0. You multiply this out, and what you get are moments for the number of primes in the interval. And this turns into the inequality between the moments for primes, for almost primes, and this one here with the tildes where it's a mix of the two, the twisted ones. And then you can work out these moments for the almost primes and the twisted primes, because we have those earlier formulas, and you find these formulas here, and you plug it in, and you get a lower bound for the number of primes at short intervals, which is 1/2 lambda plus lambda squared, whereas we expect you actually get lambda plus lambda squared, which is Poisson. We can't prove that. And that gives you this result that you gaps between that are less than or equal to half. So anyhow, that was 1990, 1992. Then Jem and I were working together, and we decided, well, if you can do second moments, why don't we try 3? So we came up with these formulas for triples. It only took about a year. And they basically give what we expect, although there were some unusual constants. We worked out the moments for these first 3, but we didn't know how to get a lower bound for third moments of primes. But we eventually discovered that you didn't need a third moment for primes. You could just take the number of primes in the interval minus what you expect and hit it with the square of one of these things. You get sort of third moments type results. And then you can optimize over the C. So when you go through that, you actually recover Bombieri-Davenport's result, and you get a new proof of the result, but it's 50 pages long, so it's not an advantage. But we did third moments, so we figured, well, let's try to do all the moments, but we didn't know how to do it, but I gave a talk in AIM in 2001, and Sarnak and Friedlander and other people sort of told us quickly how to do all these things. So we were able to work out all these correlations finally. And in cases where you raise one of these approximate primes to a third or higher power, there's some constants that come in. But anyhow, now we can work out these moments. They get sort of complicated because of those constants. These are twisted moments, other moments. You also get moments, if those constants have all been 1, you get Poisson-type moments, and the truncation just means you have an expected value smaller because of that. You can then go through all that work and start to look for primes in short intervals, and you start to get better results. So with 7th moments, you get 0.38. You can do stuff where you try different truncation levels depending on what power you're raising it to, because higher powers mean you have to take shorter truncations. We didn't know all these constants, so we just guessed them to see what effect that had. If we didn't have all these constants, we went out to like 5,000 moments, and we were actually approaching a number that turned out to be a quarter. It was proved by Michael Rogostein. And after all this experimenting, we basically were getting towards a slightly better result than Bombieri and Davenport. Now, it turns out that those multiple truncations don't actually, in the limit, don't have any effect at all. But luckily, we didn't know that. So now, step 7, we were working with these multiple truncations at different levels, and Keith Brown, who was out at AIM, said, why don't you try to figure out the right way to do it by putting a whole bunch of them in here with different levels of truncation, and try to figure out the optimum coefficients, which means that when you start trying to implement that, you start looking at divisor sums where you're truncating not individually by each divisor, but by the product. And that turned out to be such a good idea, we instantly jumped on it, but we didn't know how to pick the coefficients, so we eventually just came up with these. And then we thought we'd prove some of these results from the last year that you all heard about using this. This is just for 2, but we did it for K tuples. But then it turned out our results were wrong. So it turned out Granville and Sound found that these weights, when you squared them, actually didn't have any asymptotic formulas. So step 8, Granville and Sound also showed us how to not use moments, but just use these correlation type sums, which can do the same thing as moments, but they don't give us any of those constants, so that eliminated that. And then finally, in 2004, step 9, we were looking at a paper Heath Brown. It turns out that there's a generalized von Mongold function that tells you if a number has k or less primes. So if instead of a tuple, you just multiply these factors, k factors together, and feed it in here, it will tell you that it has less than or equal to k primes, but there's k factors, so each one has to be a prime. And it also, because of the shape of it, tells you instantly how to do the truncation correctly. So this is what we came up with. And finally, step 10, this is where we got GPY. I have 1 minute, which is perfect. The only thing we needed now was actually Pintz. So Pintz came, and Pintz realized that the thing we had there worked pretty well, but if you added a new parameter L, then that gave you more freedom because you didn't need all these guys to be prime. You only needed some of them to be prime. And with the L, you now have enough freedom to basically do everything you want. You can sum over different L's, so it's equivalent to basically having a polynomial in here. So this is the GPY method now. You use these weights, as I've described here. The detection is just about like the last one. You count the primes in the tuple minus the number that you're hoping to get. And then you put in the weight here, and you hope that this thing will be positive. If it is positive, then this sum has to have more than m terms occasionally, or else this factor would always be negative. That's the detection. And then the GPY method is that weight, that detection method, and basically asymptotic methods for evaluating those sums. And we now have about 3 different ways to do that. Now, the breakthrough in 2013 was that Zhang actually increased the size of R, the truncation, a little bit, and that was enough to go over the top. And the results of Maynard and Tao were that they actually were able to figure out the right way to actually put in the weights that we failed to do back in 2003. And when you do that, you actually get bounded gaps between not just 2 primes, but any number. So you can now prove that there infinitely often is an intervals with 70 million primes in them. And okay, so that's my part.
So I'll continue from where down that. So that the GPY method establishes the existence of small gaps between primes, then you can wonder how many of them exist. So that's another question. Now, the Hardy-Little prime tuples conjecture that Dan described, which can be this statement. We can take it as this statement. It will imply that if those gaps between consecutive primes, which are of size x, and gap size between alpha log x and beta log x, where alpha and beta are fixed positive real numbers, is given by, this is the total count of primes, and there's a factor involving the integral of e to the minus t between alpha and beta. And this result basically depends on the Gallagher result that the average value of the singular series, which was also defined in Dan's talk, is 1. Now, so this is the number of gaps that is predicted by Hardy-Littlewood prime tuples conjecture. We don't hope to prove this much, but what you can hope to prove is that if a small eta is given, fixed eta, you can try to show that these gaps occur in positive proportion. What Hardy-Littlewood conjecture would predict that this would go like eta times pi x for small eta. Now, as Dan mentioned, the prime tuple approximants we're using are these lambda sub r's, and we have this P and H, this product composed from the tuple elements, and N, and the proof of limit inferior, Pn plus 1 minus Pn over log Pn equals 0 depends on a positivity argument, that you should show that this quantity here is positive. Here theta is just the count of the primes, it's supported on the primes. And to evaluate this sum, you see log 3n is, so our n's are of size n, So this is like a constant here. So you just have to evaluate sum of lambda r squares and also sum of lambda r squared times this theta. And that's achieved by these two propositions, which are not extremely difficult to prove. And this one works for r almost the size of square root n. But in the second one, when you twist it with primes, it works for r less than or equal to n to the theta over 2. Now, theta is here, what this theta is what we call the level of distribution of primes. You see the primes, if you consider the whole sequence of primes, then you can take a modulus cube and you can consider those primes that are congruent to A mod Q. And you can do that for any residue class A mod Q, which is relatively prime to Q. And there's good reason to believe that these are almost equally distributed. I mean, there are irregularities of distribution, but they're not too bad. So then you consider all possible moduli. Remember, we're working with numbers of size roughly n, order of magnitude. So it is known by Bombieri-Vinogradov theorem that this sort of level distribution into residue classes works almost all the way up to square root of n. And that's about what, for a particular arithmetic progression, the generalized Riemann hypothesis would give. So this level 1/2 here, the Bombieri-Vinogradov theorem, is in a sense saying that giving a result that on average what the generalized Riemann hypothesis would give. So we use that, but to count from here, to get a count of gaps between primes, we have to remove this weight lambda r squared. How you remove it? Well, you use a Cauchy-Schwarz inequality to remove a weight from a sum. Now, when you use a Cauchy-Schwarz inequality, you end up having 4th powers of these lambda sub r's. And then to make the argument work, you need this kind of bound. We tried to prove this bound in 2006, but we couldn't, and then realized it probably is not true at all. And the reason is that sometimes these lambda sub r's are large, and when they are large, and you take their 4th power of a large quantity, that large quantity's effect is enhanced even more, so as to prevent this kind of inequality. So you have to take another approach. I mean, when does it become large? It becomes large when P and H has a lot of divisors. So the idea is from a work of Pintz, continuing the work of Tao and Green. Here you get the same sort of sums as we did before, but you do not count those n's for which P and H has small prime factors. You see, this is just the composition of all primes up to r to the delta. Delta is some small number, positive, which will be chosen at the end appropriately. But so here, this means that these P and H have all of their prime factors are larger than P, r to the delta. Then you get the same propositions except for these error terms. Here, so that these error terms reflect the contribution of those P and H which have small prime factors. And same for the twisted sum. And for proving like not a very explicit result, just this kind of result, you need a cruder error term. But if you want very explicit results, you need the detailed error term there. Okay, so the argument was depending on the positivity of this quantity. And what you do, the propositions allow you to evaluated in this way. And if you choose these parameters appropriately, you get this positive. So that's the limit inferior. Now you want to apply the Cauchy-Schwarz inequality here. And for that, you define this Q that's like counts only those n's for which there is a prime between n and n plus h. So, and then you think of it the other way, that for any prime difference, there are h such n's that contribute, so that you get this Q is roughly speaking h times the number of these gaps, and there's a small error term coming from the endpoint. So then you take your S, which is positive, and then you apply your Cauchy-Schwarz inequality to this. And when you apply Cauchy-Schwarz, you get this Q to the 1/2, which is essentially what we're trying to count. And the idea is now, since we eliminated those n's with P and H having small prime divisors, you can now limit the number of the square-free divisors of P and H, depending on delta. So this is the, and then once you take this number, you can bound your lambda sub r, because there are at most this many terms in this sum, and you take the maximum possible value of the interior, which is this log r to the k plus l. So you get an estimate, and the final thing comes out to be this way. I mean, if the gaps between consecutive primes, which are less than eta log n, instead of just what Hardy-Littlewood predicts eta here, we get this quantity involving eta exponentially. So there are at least this many, but this is the correct order of magnitude, so this is a positive proportional result. By just using the Selberg upper bound for Selberg's upper bound for prime tuples, you could also show, so without this theory, you can show that what we call very small gaps are not very common. I mean, by very small gaps, I mean if the primes are of order of magnitude n, the gaps between them are smaller than log n in order of magnitude. We have also some conditional results, assuming that, you know, the level of distribution holds beyond Bambieri-Vinogradov level upon half. Then you get not exponential but polynomial bounds with eta, so getting closer to the prediction of Hardy and Littlewood. And now we will be working on the same problem using the weights of Maynard and Tau, and we hope to finish this in a few months, that these, since the Maynard-Tau method works with tuples greater than or equal to 50, the prediction that we will be able to get eta to the 50 here, so there's more work to be done. And I guess that completes my talk. Thank you.
So my name is János Pintz, not to change it, we don't speak in alphabetical order, but in logical order. And I will speak just about applications of the method, so that means you don't, if you did not understand something from the previous two short segments, you should not be aware, you should not be afraid, because I begin with some applications of these methods, and so that means my short talk will be about applications of this method. And by applications, we don't think about medical or industrial or financial applications, but applications in number theory, mostly prime number theory, and I think nearly without any exceptions, application for some problems of Erdős posed usually some 60, 70 years ago. And for some of the questions, we could get answers already with the GPY method. For some of the questions, we needed to get answers by Zhang's improvement of our method, and for some of the questions, we needed the Maynard-Tower method. Here I list 3 problems of Erdős, which refers for consecutive values of some well-known arithmetic functions like dn to be equal to dn plus 1. I dot O means infinitely often, so for infinitely many values of n. This is the most famous about these 3 problems. This is the Erdős-Mirsky conjecture. To be sure, it was not solved by us, just we found a unified method which gives solution for all these problems, and in some sense stronger solutions than earlier known. So that means the Dn means that to have infinitely many pairs of consecutive integers with the same number of divisors, and then the capital omega means to have infinitely many consecutive integers with the same number of prime divisors counted with multiplicity, and little omega is the same without multiplicity, so to have infinitely many pairs of consecutive integers with the same number of prime divisors without multiplicity. And somehow it was a famous problem of Chen when he proved that for infinitely many primes, p plus 2 is either a prime or a product of 2 primes. But which one it was not possible to decide. Naturally, if he could decide that for infinitely many primes we have p plus 2 being a prime, this would be the twin prime conjecture. But it seemed to be that it's, and it still seems to be, that it is the same difficulty to show that p plus 2 is equal to the product of 2 primes infinitely often. Now this is a little bit parallel to this. The primes for which 2p plus 1 is also a prime are called Sophie-German primes, and the same method gives that for infinitely many primes we have either 2p plus 1 to be a prime or to be a product of 2 primes. And if this conjecture would be true, then it's very easy to see that 2p and 2p plus 1 have both 2 prime factors, and then they have both 4 divisors. So we should have even, so to say, for all 3 functions here, we would have these conjectures of Erdős and Erdős-Mirsky to be true. Now, unfortunately, this that we don't know whether 2p plus 1 is equal to a prime or a product of 2 primes. This has some deeper roots in number theory, and this is the so-called parity phenomenon of Zellberg, which means, roughly speaking, that sieve methods alone cannot distinguish between numbers with an odd or even number of prime factors. Now, Erdős conjectures were considered, so to say, as difficult as the twin prime conjecture for a long time. Once it was solved with a different number, so that means that n plus 5040 has infinitely many times as many divisors as n, so that came already somewhat close to the Erdős-Mirsky conjecture. And really 3 years later, Hisbraun proved the Erdős-Mirsky conjecture. And but to tell the truth, he could not specify this common value, and even he could not specify the parity of this common value. And all this was due to this Zellberg parity barrier or parity phenomenon. And then it took another 20 years to prove the same for the little omega function, where we consider numbers with prime divisors counted without multiplicity. And I will mention later on how our method could be applied for this type of problems. But just as an introduction, I mentioned that together with Sid Graham, we succeeded to show that if we consider, instead of primes, numbers with, not like Cem, with at most 2 prime factors, but like, I mean not like nobody, with exactly 2 prime factors. We introduced this notation E2 for numbers with exactly 2 prime factors. Then we have infinitely often a bound that moves 6 between numbers with exactly 2 prime factors. And earlier problems with exactly 2 prime factors seem to be as difficult as problems with primes themselves. Now, I list here a few results that, for example, if B is any number at least 0, then we have simultaneously all these equations could be true for infinitely many values of n. So we can solve the conjecture of Erdős-Bielski and Erdős simultaneously for all 3 equations, so to say, for the same infinite set of numbers n. And we can specify the value of little omega, capital omega, so this common value for these arithmetic functions, and they can be quite small. So for we have, as you see there, we have, for example, different number of prime factors have to be at least 4. Prime factors counted with multiplicity have to be at least 4. This has to be at least 5. And even we can go further. This means that we have infinitely often 2 consecutive numbers which have each exactly 3 prime divisors. And I showed also here a general theorem which uses the Green-Tau method, namely that these relations are not only true for infinitely many number of n, but this infinite set of numbers n, which satisfies either 2, formula 2, or 3, or 4, all these sets contain arbitrary long arithmetic progression, similarly like the primes. So that means we get something more than just infinite sets of integers. Now to go some ideas behind the proof, I will even tell a short proof of this, one of these results here. But the basic theorem, which is relatively long, maybe 20-30 pages long, is the basic theorem that if we have 3 linear forms without, so that the product should have no fixed prime divisor, then we have at least 2 of these forms which have exactly 2 prime divisors for infinitely many values of n, and additionally we can prescribe that all of these prime divisors should be larger than a given arbitrarily given constant, or even n to epsilon or something like this. But in our application, in the proof, this constant will be just 3, so it's not needed to be too large. And a corollary of this is that if we take these 3 linear forms, n plus 2, n plus 6, then it's clearly that this is an admissible triple, and in this case we have difference that moves 6 between consecutive numbers with exactly 2 prime factors. Now, the proof of this theorem that we have infinitely often 2 consecutive numbers having exactly 3 prime factors is just a few lines long. If we consider 3 simple linear forms, L1m, L2m, L3m, as given in the second line, then this is clearly admissible. So if I take m equals 0, then the product is equal 1, so has no fixed prime divisor, clearly. And then we have still these three relations among them. So for example, if we suppose that L1 and L2 both have 2 prime divisors exactly, larger than 3, then this relation that 4 times L1 and 3 times L2 are neighboring integers always. And if L1 and L2 have exactly 2 prime factors, then clearly 4L1 has 3 prime factors, 3L1 has 3 prime factors as well. So that means this solves the problem in a few lines. And I have to add that this original solution of Schlager-Kuchta, this needed also some work with computers and some numbers with some 20 digits or so. So that means it was quite different, the proof. Now if we go further, I mentioned some important results of Maynard and Tau. The first one refers what was mentioned by Dan, that we have infinitely often bounded gaps between blocks of primes. The second, that if we consider in some sense the original goal set by Dixon in 1904, that for K linear forms which are admissible, these n plus hy should be, by this notation I mean that simultaneously primes infinitely often, then this is true at least for a positive proportion of all k tuples, whatever this should mean exactly mathematically. Then here are some results. The original result of Maynard reduced the gap between consecutive primes to 60, and then there's a lot of computation and a lot of new ideas by the polymer project of Tau. This was reduced to 246, and actually Tau gave parallel to Maynard basically the same, so to say, he proved the same result with somewhat different methods. And then finally here is a conditional result. If primes are very regularly distributed in arithmetic progression, then we get even 12 as a difference infinitely often. Now we go to other problems about large gaps between consecutive primes. And here, if you take a look for this picture, for this few results, then you can see just from the dates that all this progress was done in 10 years, and basically the end result was this Erdős-Rankin function Gn, which is roughly speaking log n. So if you see this log 2n, this doesn't mean log n base 2, but it means log n. Log 4n means 4 times iterated log n, so log n. And so that means basically this was the result of the state of art in 1938, and then it was Erdős offered $10,000 for this in 79 to be improved, the highest amount ever offered for Erdős for a mathematical problem, but this did not help too much. We could improve Meyer and Pomeranz with 30%, the best result, and I could improve the best known result, and then I could prove with another, roughly speaking, 50% more, but by this we didn't earn any money, despite Erdős was already dead at that time. So, but not this was the only handicap of it, or only reason for it. Now, if we consider chains of large gaps between consecutive primes, then the question of Erdős was whether we have not just one big gap between consecutive primes, which is as large as, so to say, log n times infinity, but whether this is true for a block of k consecutive primes for every gaps and then Erdős proved it for k equal 2, and then Helmut Mayer, using his famous matrix method, proved it for an arbitrary value of k, plus the size of the gap was exactly the Meyer's result, the Erdős-Rankin result. Now, here concerning the normalized value distribution of Dn, there is another problem of Erdős, that Dn divided by log n is everywhere dense in 0 infinity. And despite they could show that this has a positive density, they did not succeed to find any number which belongs to it. And our result shows that the 0 belongs to it. And I could improve this using Zhang's idea that with an ineffective C, a whole interval around 0 belongs to this set of limit points of Dn over log n. And I could generalize it the same result for basically for nearly every function which tends to infinity and which is not larger than this Erdős-Rankin function. So that means this still doesn't solve the $10,000 problem. And so theorem 6, this is the generalization that for interval we have this. Then theorem 7 says that basically if I consider infinitely many functions which differ a little bit from each other, so fi plus x divided by fix tends to infinity, then we have 0 to infinity, the whole interval appears as a set of limit points, which means that to every function we have another function very near to it for which this is true for the whole interval. Now, if we go further, another problem of Erdős was whether the Dn plus 1 over Dn, the limit and lim-sub, are 0 and infinity respectively. And I could prove again this in 2013, then later in 2014 with this function Gn. So that means even their ratio is not only infinity but as large as the Erdős-Rankin function. And then later I could show that k, an arbitrary number, let's say of m gaps, can be as large, so each of them can be as large as any given function which is not larger than the Erdős-Rankin function, roughly speaking. And this includes both the result of Mayer about chains of large gaps, and this contains actually, if you think a little bit, also the minor tau result that we have arbitrary long blocks of bounded gaps between primes infinitely often. And to finish, I can tell still that even what we could do a little bit more, so that means that k small gaps, and then left and right a big gap, and the ratio is again the Erdős-Rankin function. Thank you very much for the attention.
Okay. Thank you very much for this nice, wonderful presentations. So let us thank to the three speakers again.